So in this video, we're going to talk a little bit about what goes on in a tension test and why we would want to use an extensometer and not use the displacement data or the crosshead displacement of a testing machine. So in some previous videos, I showed how to build the specimen for use in a finite element analysis, and we did some calculations in Abacus using this. And in this video, we're going to analyze these results. We have a couple key locations on here that we want to take a look at. There's a node that I have labeled as 576 and 510. If I were to put an extensometer on here with a 1-inch gauge length, this would be the location of that extensometer. What that extensometer does is it measures the change in length over that particular gauge length. And just to kind of denote what this is the change in gauge length, the change in length for the extensometer. Now, this being a tension test, in a testing machine, an electromechanical testing machine, would control this in what's called displacement control. So the bottom part of this would be gripped, and the top part of it would be gripped, and depending on how your testing machine is set up, the way mine is set up, the top moves upward and the bottom stays fixed. So I'll indicate this with the grips being here and here. And when you do a tensile test, you have a little bit that of this large gauge section that you usually would have sticking out of the grip, and then you have this necked, or not necked, but reduced section through this radius of curvature into the gauge section and down here. Now some key information. The length of this gauge section is 1 inch, or 25.4 millimeters. Node 576 is at the top knife edge and 510 is at the bottom knife edge. The total distance of the uniform section is 2 inches, or 50.8 millimeters. And I did a distance measurement, and I got a distance measurement between the top and the bottom grip. Let's see what that was. I think I still have it on my hypermesh screen, of 80.32 millimeters. Okay, so this is a distance between two nodes. So 80.32 is the distance in between here and here. All right. There's going to be an equation that we need to use. We're going to use sigma is equal to E epsilon. We're going to use epsilon is equal to delta L over L original. And any kind of combination of these things we're going to end up using. So we might rearrange this to solve for the change in length and so forth. All right, so let's get in to look at the values of the displacement of node 510 and 576. So I'm going to go into Abacus. I'm going to turn on displacements. Now I'm looking at a step 1, an increment 1, a step time of 0.1 in my analysis, where the stress is this value for the red zone. Now we're going to probe these values to find out exactly what the stress is in just a moment. But let's change this into displacement, and we want the displacement in the 2 direction. See, it's fixed, that's why it's blue. There's no displacement down here, but we have more and more displacement towards the top. And let's see, we're going to take a look. We're going to query this by probing the values for a keyed in node. And my first node is 576, and my second node is going to be 510. Okay, so those are the 2 knife edge values. So here's the U2 displacement, and what I'm going to do is I will just screenshot that for reference. And paste that on here. Alright, so 576 is the top, 510 is the bottom node. If I take the difference in those two nodes, then I have the relative change in displacement between those is the change in length between those 2 points. So let me see if I can put these in my calculator and get a good number that's precise enough. 0.0693363 and 0.0306564. I'll take the difference. So the change in length over the gauge length of 25.4 millimeters is 0.0386799 millimeters. And I got that by taking U2 of the top minus U2 of the bottom, 2 being the vertical direction of the specimen. So if I wanted to calculate strain that the extensometer would read, then I would take that value and divide that by 25.4 for my 1-inch gauge length extensometer. Now in microstrain, I would have 1523 microstrain. And since I'm using aluminum, and I use the value of 70 gigapascals, that should correspond to a stress in the axial direction of, let's see, that would be 70 times 10 to the 9 times that value of strain, or 106.6 megapascals. Let's see, 106.598, 106.6 megapascals. All right, let's go back to our abacus model. I'm going to change this value to stress. We'll go ahead and write that to a file. And we're going to look at the stress in the 2 direction. And we can look at the 510 and the 576. All right, so that's exactly what I had, 106.598. We can write this to a file, and we can change this to the strain in the 2 direction for 576 and for 510, and we got 1522.84, and I had 1523 microstrain, so it's the same value. Okay, so everything looks pretty good as far as that goes. Let's put maybe a check mark by this. So if you were to use an extensometer in the lab and your modulus of elasticity was 70 gigapascals for aluminum, maybe it's 69, maybe it's 72, but if it was exactly 70 and everything went exactly right and you had a perfectly calibrated extensometer, then you would have a stress level 106.6 megapascals, a strain level of 1523 microstrain. Well, what happens if you decide that you're not going to use an extensometer? Here's where the problems start to come in. What are you going to use for a gauge length? And how are you going to measure things? Well, in a testing machine, if you don't use an extensometer, even if you do use an extensometer, you're usually measuring the crosshead displacement. Now, the crosshead displacement that we have in this particular case, we'll call it delta L C for crosshead, was 0.1 millimeters. We can verify that. We can go back to our abacus model, look at our displacement in the 2 direction, and look at a point up here. We can select from the viewport. There we have a 0.1 millimeter for U2. Okay, so now that's the change in length. What do we divide that by? And what kind of strain do we get out of that? Let me use black. Well, maybe we use everything in between those 2 grips. So that's 80.32 millimeters. Let's see what we get. I get 1245 microstrain. Now look, you might look at that and say, well, 1523 versus 1245, that's not a big deal. We'll see that that actually is kind of a big deal. If we were to use this data to try to calculate a modulus of elasticity, we're going to be kind of far off. Okay, so why did we get, why are we using 80.32? That's everything that's exposed that has a chance to stretch out from the grip, between the grips. Another thing we might use, I'll just put maybe use, well, this is stiffer here where the cross section is bigger, so maybe we should just use the 2 inches. Maybe we should just use the 50.8 millimeters. I'm going to take 0.1 and divide it by 50.8, and I get 1969 microstrain. All right, let's do some calculations using those numbers. Let me make a little bit of room. All right, so let's draw the initial portion of our stress strain curve. And we're doing this in the linear elastic region. So we have sigma and we have epsilon, and we have it just perfect where we start off at 0 strain and 0 stress, and we load it up, and this is the modulus of elasticity for aluminum that we used, and it's exactly 70 gigapascals. And for our stress level of 106.6 megapascals, that corresponds to a microstrain reading of 1523. Let's just check that real quick. If we rearrange sigma is equal to E epsilon and solve for E, E would be equal to sigma divided by epsilon. Now I know I'm going to get the right answer, but let's go 106.6 times 10 to the 6, and divide that by 1523 times 10 to the minus 6, and I get 69.99. I get 70 gigapascals. Okay, so that checks out. So what happens when we have this crosshead displacement of 0.1 millimeters and we divide by the total distance in between the grips, we get 1245 microstrain. That's a smaller value of microstrain. But my load cell is pretty good. My load cell will still tell me that I have exactly 106.6 for my stress. Load cells are very accurate. So what we've got is we have a stiffer estimation of what our modulus of elasticity would be. Okay, so let's calculate our crosshead modulus of elasticity value. 106.6 megapascals divided by 1245 microstrain. I end up with 85.6 gigapascals for my modulus of elasticity. That's kind of far off from the accepted value of aluminum. Okay, so that's not a good thing to do. All right, well, what about our other thing where we ended up just using the uniform gauge length of 50.8 millimeters at 2 inches? And we'll just say, well, all 0.1 millimeters of displacement went through that and nothing else deformed. Okay, in that case, maybe we would use a different color. We're way over here, but we still have the same level of stress because our load cell is still real good. So we're over here somewhere, and I'll put this as E 2 inches. The stress level is still 106.6, but now we're down here at 1969 microstrain. So 106.6 megapascals divided by 1969 microstrain. I get 54 point, let's call it 54.1 gigapascals. So I'm still pretty bad. I don't know if you could take the average of those and get close. Yeah. So the point is that if you're doing a good tensile test, you want to use some form of extensometry over a gauge length that has a uniform strain distribution along its length. So what happens is the strain distribution does not stay uniform when we get into the radius of curvature. We can examine that with our abacus model. We'll go back to here. And close this out. And let's make this a little prettier. Maybe just put feature edges on it. Let's look at the strain distribution in the Y direction. And maybe we can cut this and look at a cutting plane. So let's look at options, view cut. Let me find the right option here. No, I think this is one down here. Okay. So that'll cut that in half. We can spin this around, kind of look inside of the specimen. See if we can make the viewport a little better. All right, so in between those two nodes, we have a pretty good uniform strain distribution. When we get into this radius of curvature, we start to get a little bit of a non-uniform strain distribution through the thickness, and of course definitely along the length. The strains change quite a bit. In this thicker section, the strains are a lot smaller, getting down from 1500 microstrain down to maybe 25 microstrain. So they change quite a bit. We can look at the stress distribution as well. And we, again, in the same places where we have a non-uniform strain distribution, we have a non-uniform stress distribution. Now, of course, what is the limit when you do a tensile test as to when you have a uniform or non-uniform strain distribution, even in this gauge length? Well, when the specimen starts to neck, then you have a localized high strain region. You have a non-uniform strain distribution. So once that specimen starts to neck, then your extensometer reading, if your extensometer encompasses the neck, is going to be off just as bad as anything else. Pull that extensometer off. Of course, once it begins to neck, you have also a big enough change in geometry that you have some weird things going on with your stresses too. All right, so let's kind of recap. You can do all kinds of things to calculate strain, but if you want to do a good test to get a good value for a modulus of elasticity, a material stiffness, then you have to have some precision and understand how you're collecting that data. When I review technical papers, I'll often see people use weird values to come up with strain, weird gauge lengths, because maybe they're using a really tiny specimen and they don't have a really tiny extensometer. In those cases, you really have to use some kind of optical technique to measure the strains.